In this video, I'm going to explain about scalar and vector magnetic potentials. So we have learned more information about electric potential, that is V. V is electric scalar potential. This V helping us a lot in solving many electrical problems. So most of the time, from the charge distribution, we find electric potential. From the potential, we find electric field, then flux density if needed. Then we continue up to the capacitance if needed. So the first calculation goes with electric potential only. The very advantage of this quantity is it's a scalar. So direct calculation of electric field E from Q, the charge distribution, is very complicated. So V simplifies the computational complexity of E. So V is widely appreciated and widely used in electrical circuit analysis. So now the question comes that can we define a similar scalar magnetic potential? Is it possible to define a scalar potential for magnetic field? Is it there? So that we can also solve the problems of magnetic field in a simple way. So let us start working upon this. The electric potential is given by the electric potential, that is V scalar, is given by the relation E is equal to minus del V, negative gradient of potential. This is the fundamental relation between electric field and electric potential. So let us define ourselves a relation similar to this for magnetic field. That is, let in place of electric field intensity, we shall consider magnetic field intensity, negative gradient of a scalar potential V. Let us assume that this equation exists. This holds good. And here Vm should represent scalar magnetic potential. So this equation is just written based on the knowledge of electric potential. Let us say equation number 1. If this equation is valid, if equation number 1 is valid, then it should satisfy the curl and gradient of the magnetic field. Then only we can accept the existence of this scalar magnetic field. Let us consider the very well-known Ampere's law, which is basically curl of magnetic field. Curl of magnetic field, that is, the curl H is equal to J. So the validity of scalar magnetic potential is tested with this curl equation, which is already proven. So if I put minus del Vm in place of H, then let us see what happens. So from the mathematics, vector algebra, we have an identity. What is that one? Is the curl of a gradient is always 0. All right. So here is a curl and this operation is gradient. So curl of a gradient is, for any vector for that matter, curl of a gradient is always 0. This is a vector identity. It's prone in mathematics. Curl of a gradient is always 0. So therefore, from the above equation, we get a relation J is equal to 0. So that means J is the current density. So no current. That means current free region. You look back once again. Del cross H equal to J, curl H is equal to J is the Ampere's law, which gives the relation between the magnetic field developed by the current J, right? So, but after introducing the scalar magnetic potential concept into this one, we got J is equal to 0. That means if at all, if scalar magnetic potential is existing, that is existing only for the regions not containing current. So current free regions can use this idea of electromagnetic potential. See, in electromagnetics, there is a huge space where magnetic field is available but not containing current. For example, if you have a current carrying conductor, let us say I, then field can exist inside as well as outside the conductor. Outside the conductor is the space where Vm is existing, but this Vm cannot exist inside the conductor because there is current flowing through it. That means, therefore, Vm can exist in current free regions. We know that in electromagnetics, electromagnetic waves are considered in free space. They're traveling for larger distances in free space where there is no current. That's why the Vm is going to be largely defined in electromagnetics. And also in permanent magnets, the permanent magnets, also Vm can be used because no current flow takes place in permanent magnets. So that's why Vm is a very useful quantity. So this information is obtained from the curl of the magnetic field. Similarly, if I consider the divergence now, consider the divergence of magnetic field. You consider any vector related to magnetic field, then its divergence should be used to verify for the existence of V. In magnetic field, divergence of B equal to 0 is a very well-known equation. And this is the Maxwell's equation, and this is also the Gauss law of magnetostatics. So this is a very important equation in magnetic field. So here we can use this equation to verify the existence of Vm now. Right. And Vm is related to H. So let us convert B to H. So B is equal to mu H. So mu cannot be 0. So then divergence of H must be 0. So in this equation, if I substitute this scalar magnetic potential relation, then we get an equation. What is that one is? Del dot del is del square Vm is equal to 0. You must be knowing this equation, which is discussed in electrostatics. So that is called Laplace equation. This is the Laplace equation where del square Vm is equal to 0. The Laplace equation is applicable for the space or the regions where no sources are present. So something like current for magnetic field, charges for electric field. So for source-free region, that means no current, no charge region, Laplace equation is valid. That means your scalar magnetic potential is existing, can be used everywhere where there is no current source. So this throws a light. This throws a light on presence of scalar magnetic potential. But now question comes to our mind. What about the region where current is present? Is potential present in the region where current is present also? So this is the question to be answered. So what to do with the region where current distribution is present? Okay, this is the conductor, and this is insulator. In both the media, magnetic field is present. But here, conductor contains current, insulator contains no current, but this current produces this magnetic field. For this region, we have defined scalar magnetic potential. What about this region where current is present? Then let us continue our discussion and let us work out the possibility for this point number 2. What to do for current region? So for that, let me consider this relation again. So divergence of vector B is equal to 0. We have a vector identity. Which helps us. Vector identity, that is divergence of a curl is always 0. This vector identity is available in vector algebra, according to which divergence of curl of any vector is always 0. So based on that, can we define a potential which is applicable for region containing the current? So if I proceed in that way, let us define, let B is equal to curl A. In this case, we don't know what A is, but this A later will be defined as vector magnetic potential. If at all, if A is acceptable, then this becomes a magnetic potential, but it is a vector, so it becomes vector magnetic potential, which is applicable to the regions where current is flowing. So then what happens then? Therefore, divergence of the curl A is equal to 0. So this equation satisfies this identity as well as this Maxwell's equation. So we have to examine the existence of vector magnetic potential again in the same way as we did for scalar vector magnetic potential. That means we shall consider the curl of this one and as well as the divergence of this to check the existence of vector magnetic potential. Now we shall consider the Ampere's law, that is curl of magnetic field here. So now we have to introduce A into this equation, but A is present inside B. Let us consider H to B. H is equal to B by mu. So curl B is equal to mu J. This is the Ampere's law in terms of B. Now let me introduce A here. B is equal to curl A is equal to mu J. But here double curl is not zero. Curl of a vector is not zero, but it can be expanded. So the curl of A can be expanded as del into del dot A minus del square A is equal to mu J. So the expansion of double curl is taken from the vector algebra, which gives us this relation. So in this case, there are two terms which are very useful for us. One is divergence of A. So point to be noted. Divergence of A, that is, this information about divergence of potential, divergence of vector magnetic potential is not at all available anywhere in the literature. If you refer to any of the electromagnetic references, the information is not available. But in basic physics, the information about divergence of vector magnetic potential is available, according to which this is going to be zero. So we shall not go in deep about this at this point of time. So we directly take this concept from the physics and we continue taking this one. So the divergence of vector magnetic potential is zero. So that means divergence of A is available in one or other form. Next, we shall look into the other one. If this is zero, then we are going to have minus del square A is equal to mu J. Del square A is equal to minus mu J. If you observe this equation carefully, this resembles our Poisson's equations. Poisson's equation, where you recall we proved that del square V is equal to minus rho V by epsilon. Look at the analogy. Del square V is a electric potential, A is a magnetic potential. Here. Both of them are having Laplacian. Del square is equal to minus J is the current source for A, rho V is the charge source for B. Electric field is explained with permittivity and magnetic field with mu. Okay, so look at this. That means the curl of A, is giving some useful relation, that is Poisson's equation itself. So divergence of A is defined. So if you take A separately, its divergence is clearly defined as 0 and its curl is defined as B. That's why the vector magnetic potential is also considerable in magnetic field, and this is used in many applications like antennas, wireless communications, many applications to define very useful concepts. Right. Next, at the same time, I can write some solutions about this vector magnetic potential with the knowledge of scalar electric potential. Okay. Now consider this relation del square V minus rho V by epsilon. So from this relation, we can conclude that rho V is volume charge density, which is present at a point. Then electric potential is produced at a distance of r, let us say. So we know that in electrostatics, you have studied many applications where charge is present at one point and electric potential is measured at another point. And if r is large compared to the volume of this charge, then this can be assumed as a point charge. We know that any volume charge distribution can be assumed as a point charge if the distance of measurement is very large compared to its size. So therefore, we have a relation V is equal to Q by 4 pi epsilon r. This is the relation between electric potential and the charge producing it. Here, Q is the volume charge distribution, which is present at a very large distance. So based on this idea, I can give you the solution of vector magnetic potential from here. So this relation, let me copy this relation here. Okay, the solution of A is given by. So what is the solution of A is given by? So write this equation very close to this one. So what is that equation? Del square A is equal to minus mu J. So compare these two. In place of E, A is there, rho V, J is there, 1 by epsilon, mu is there. So therefore, the solution of A, keeping this point in mind, we can write that A is equal to Q is the point charge given by this equation. Similarly, here also we can have volume charge integration that is equal to Q is the point charge, but in magnetic field we can take it as current element, IDL. In electrostatics, we consider the smallest element of the source as point charge. Here, differential current element is chosen. Denominator 4 pi, R is R, 1 by epsilon is equivalent to mu. So mu I dl 4 by epsilon is the solution for vector magnetic potential, which has the dimension of Weber per meter. And this equation is directly coming from this relation, that is V is equal to, in place of Q, imagine rho V dV divided by 4 pi epsilon r. Now compare these two solutions. This is the solution of scalar electric potential, and this is the relation of vector magnetic potential. Rho V becomes I dl dV 4 pi epsilon r. So this relation is very much used in evaluation of magnetic fields in space, which are farther distant from the sources. So this discussion is throwing some light on scalar and vector magnetic potentials, right? That's about it. Thank you.